Okay. Good afternoon, everyone. So welcome to the last lecture of this series. So time only goes one way. So this is the last one, and yeah, I hope you really enjoy it and get engaged in it, also inspired from it. Okay. So let's welcome Frank Wilczek.
Well, if I've done my job, you should be pretty well motivated to hear about axion properties and how we're going to try to find this particle in nature. So without further ado, I will launch into it. Many, although not all, the experimental strategies are based on the interactions of axions with photons. And that's what I'm going to focus on. The Lagrangian density from which all else follows is the one dictated by the triangle anomaly and the basic properties of axions. We get the triangle anomaly for the strong interactions involving gluons because the asymmetry is arranged so that quarks have Peche-Quinn charge, or we can just postulate that coupling. But it's very natural also, and in detailed models one usually finds, that there's also a coupling of the axion to the electromagnetic field of the same form, which can arise from the triangle graph or other sources. And if you're dealing with a unified theory, this comes automatically. You get couplings to gluons together with couplings to photons, and to W bosons too, but those are not significant phenomenologically. So from this, we derive a form of Maxwell's equations with additional terms, where the electric and magnetic fields are driven or coupled to axions in very predictable ways. And this leads to some remarkable qualitative effects. It means that if you have a gradient of the axion field, then a B field here produces a term on the right-hand side of the Maxwell's equations, which would be exactly what a charge does, what a charge density does. So who should you ask what's a charge better than the electric field? And the electric field says that this is a charge density. So in the presence of the gradient of an axion field, a spatial gradient, a magnetic field produces electric charge. The other additional terms here are generating in the same way currents, right-hand sides of the del cross B equation, and we see that in the presence of an axion field with changes with time, which is what we get in cosmology, because remember, the axion field oscillates at the mass of the axion. So we get this kind of thing, and that means a B field induces a current, an electric current, and a gradient axion field here, a spatial gradient axion field, induces a kind of Hall effect. It means if you have a spatial gradient of the axion field, then an electric field produces a perpendicular current. So each of the additional terms has a nice intuitive interpretation. This one is particularly important for the axion experiments I'm going to talk about, because it's very convenient to produce big magnetic fields. So you can produce a big magnetic field, and then in the presence of that field, the time variation of the axion field, which is much larger than its spatial gradient. The axions are produced at rest. I didn't discuss this in detail, but I alluded to the fact that the field is approximately constant in space. The quantitative measure of that is that this gradient term is about 1,000 times smaller than the time derivative term. Or a way of interpreting that in terms of particles, if you consider the axions as particles, this is representing the mass of the axion particles, and this is representing their momentum. And the momentum is about a part in 10 to the 3 of the mass. That's connected with the fact that the velocity, typical velocities of the axions, is about 1,000th of the speed of light. And that's connected with the fact that the escape velocity from the galaxy is about 1/1000th the speed of light. So the axions, viewed as particles, fall in and rattle around the galaxy, and that's how they get their velocities, even though they were produced very, very cold. So, in the presence of a background magnetic field, an axion field, I mean the axion field that we expect on the basis of cosmology, that background axion field mixes with the photon, you could say. It occurs in a linear form within the equations for electric and magnetic fields, so it can be considered a mixing. And it pumps energy, because it's time dependent, it pumps energy into electromagnetic fields. So that suggests a detection strategy. We want to design antennas to encourage the pumping. The axion couplings, as we've discussed, are very, very small. So we need to do everything we can to get a detectable signal. That means we have to use any trick in the book in order to do that. And also we have to be very good about using low noise amplifiers and state-of-the-art technology all the way around. Okay, so with that background, I'd like to discuss an experimental project that I've been heavily involved in that's brought some new ideas to the subject and seems to be is actually under construction and is a very, I think, to me, a very exciting project. So this is called the Alpha Haloscope project. And here's a picture of the experiment. Just, let me get my coffee, I'm sorry. It's a little simplified. This is the idea of the experiment. It's based directly on those equations of axion electrodynamics. And you have a background magnetic field. And in the presence of a background magnetic field, you have the coupling axion B dot E. So the axion in the language of Feynman diagrams, translating that into Feynman diagrams, it's the same content as those Maxwell equations. But you find that axions can convert into photons. and we know how to detect photons. So that's the overall strategy of the experiment. You fill a box with magnetic field, and axions will convert to photons, and then you use techniques to detect photons. So the essential ingredients of this experiment are a magnet, an eye, and a box, which in more scientific terms are a magnet, a sensor, of course it's not going to be a human eye, as you'll see, and a resonator, because you want the box to encourage this process. And we'll discuss how that's a non-trivial issue, that how to do that best or efficiently. So here, it's going to be a very weak signal looking ahead. So we want a big magnet, and this is the magnet which we hope to use in the long run. In the medium run, we have a somewhat smaller magnet, but this is one that's being shipped over from Germany. It's 15 Tesla, 100 centimeters bore, and about a meter wide, filled with that kind of field. And the sensor is not an eye, but a low noise, quantum limited, fancy, modern device for detecting radiation in the microwave region. Remember, the region we really want to study is several gigahertz, maybe tens of gigahertz. Now, but and those are important technologies to manufacture big magnetic fields and to develop and to detect microwave photons. But they're used for many other purposes and have been highly developed for many years. The characteristic challenge as far as axions is concerned is the resonator. Getting a resonator that enhances the probability, the efficiency of axions turning into photons. As the name suggests, a key idea for a resonator is you want to exploit resonance. Okay, so your axion field, in terms of energy and momentum, is oscillating at its mass, that's the energy, but its momentum is essentially zero. It's 1,000 times smaller. So its energy and momentum look schematically like that, whereas a photon has to have E squared minus P squared equals zero. The photon is massless, and so its dispersion relation doesn't fit, and so there can't be resonance unless you help it along, unless you somehow repair this mismatch. So one strategy to do it, which was exploited in many experiments, is to give axions momentum using cavities. So remember, Noether's theorem says that if you have a uniform in space background, that momentum is conserved. If you have a background, a cavity, that affects electromagnetic fields, and so affects this force, or affects or a magnetic field that's confined in space, that has that momentum, non-zero momentum. The background is not uniform, and so it can convey non-zero momentum to the axions or the photons, wherever you want to locate that injection of momentum into the equations. So that's a possibility. Give the axion or the background a momentum so that this can match. But that has a limitation. That is, you've made the box small because you want to use it to convey a big momentum on this scale, as big as the mass of the axion. So a different approach is instead to give the photon a mass. That has the advantage that you can have an arbitrarily large volume in principle once you've given the photon a mass. Now, what photons are famous for having mass, for not having mass, rather, for being massless. But there are well-known physical situations in which the photon obeys the equation of a massless particle, or we might say it acquires a mass. One is in superconductivity, where the equations for photons inside superconductors are literally the equations for a massive spin 1 particle. And the characteristic properties of superconductors actually mostly follow from that very fact. And this was a model for the Higgs theory of how W bosons get made. So that's very well known, even if not always phrased this way. However, that won't quite work here because we want to apply a very large magnetic field, and a superconductor will not be happy with a large magnetic field. Another situation in which photons get mass is inside a plasma. You have the plasmon phenomena and plasma masses. But we don't want to use a gaseous plasma, such as you find in neon signs and things like that, because that's a very noisy environment, and we're going to look for a very weak signal. So that's not going to work. However, there's a very cold plasma that's widely available, namely the plasma of more or less free electrons inside a metallic material. So that's a way of getting the photons to have a non-zero mass by filling your resonator with that kind of cold plasma. However, if you look at the parameters typical of metallic materials, you find that the masses that they have, the photon masses involved, are too big. Basically, the reason that metals shine is that the mass of a photon inside the metal is larger than the momentum available in light. And so the photons can't get into the light, they bounce back. Can't get into the metal, they bounce back. Okay. That means that the mass is not in the microwave region, but in the visible region, and it's actually in the ultraviolet region. Well, ultraviolet light will typically shine through metals, but it's much, much larger than we really want for axions. So, what do you do about that? Well, instead of taking a big block of metal, just take a lot of wires. I said that. So the alpha strategy is to exploit plasmon-like resonances in a wire metamaterial. So that was the original idea. So that imparts mass to the photon, and if you fill your cavity with a wire array, that gives the mass to the photon and relieves the constraint on size. Another very advantageous feature is we don't know what frequency we're looking for. So we want resonance, but we want to be able to tune it like a radio so it can pick up signals at different frequencies. And here, the spacing between the wires is something that's fairly easy to adjust, or at least to think about adjusting, and that enables you to tune the mass, and so be sensitive to resonance at different frequencies. And this is an early prototype. If you look carefully, you can see the wires in here. And these things have been tested out. They seem to work very nicely. Okay, so I'm happy to announce that as of a few weeks ago, but we were told informally that this was going to happen about a year ago. The Alpha projects have been funded and is actually now being constructed by a consortium of very distinguished foundations and many institutions. Whoops, let me go back. Many institutions in the United States and also elsewhere are involved. And this is what the proposal said we would do here. This is the gold band we looked at before of Axion parameters. And this is the cosmologically favored range where you see you predict that the axions produce 100% of the dark matter. Okay. Now, because we wanted to get this funded, we were, I think, conservative in our estimates, and this is what we've sort of promised to deliver, but I think I'm not so conservative. I think we can do better, both in terms of sensitivity and even the range of masses. So this is where it's going to happen. This was the first group meeting about a couple of months ago at Yale, and there we are. So that's the basic idea of the Alpha project, which is now being built at that Wright Laboratory at Yale University. Here are some possible enhancements that we're exploring, especially with my group at MIT. So there are ideas to enhance the resonators in different ways, and there might be other ideas. You're very encouraged to think about it. This is an area of kind of exotic electrical engineering that physicists don't often do, so maybe we're missing something. So one idea is to use dielectrics in place of magnetic wires in periodic arrays. So that's a way of taking your photon and supplying K by having what's called a photonic crystal, and that can cancel off this K and again achieve resonance. And you can adjust the geometry of the array to tune it. So here's a design based on that kind of idea. But there's plenty of room for optimization. Here's how you might move the array by having the whole thing mounted on this clever array of rigid squares. The rods are on that, and you adjust the rigid squares, and the array gets bigger or smaller. Another idea that I think is very exciting, very promising, I should say, is to fill the cavity not only with wires, but also with soft paramagnets or split ring resonators, which are kind of things that mimic soft paramagnets, but are a metamaterial that's maybe less lossy. The basic idea here, I'm in trouble. I need help. Okay. Where were? Yeah.
You want to go disappear the mouse? Oh, yeah. So, yeah.
Just full screen.
Yeah. Oh, we're way past here. I think we're on a completely oh, no, here we are. Okay. Here. Okay. So, the basic ideas are, if you consider not the free space Maxwell's equations, but allow for permittivity and magnetism, and what they I can never remember what these things are called, but anyway, epsilon and mu, like this, then this is the driving magnetic field, but the response here has a 1 over mu, and therefore, if mu is very large, it's as if the axion field or the magnetic driving background field were big. And the mu's can be quite big. They can be thousands or hundreds of thousands in soft magnets or in split ring resonators. So that's a very interesting direction. And well, we're also exploring ways of channeling the static B field into tubes where it has a larger value. But I don't. That would be a kind of digression to just discuss that in detail. So keep calm and watch this space. I think we, in the next several years, will have, unless something goes very wrong, we'll have definitive tests of the axion hypothesis in the standard cosmology. Okay, so that's a natural place to pause. Oh, no, it isn't. No, well, it is a natural place to pause. So let me take questions at this point about that's kind of the high point probably of this part of the lectures. And
yeah. So Frank not only talk about theoretical parts, but also the experimental progress on the axion detections. So any questions?
Yeah.
Frank, you mentioned that in the Alpha project, they need a very big magnet. I'm wondering.
Very big what?
Magnets.
Magnets, yes.
I'm wondering, for example, in the astronomical case, for example, the neutron star, it have a very large
Yes.
magnetic field.
Yes.
And could we see something similar to the experiment on the neutron stars?
Yes, there are. Well, in fact, the gentleman in the front row here were telling me earlier. Maybe I'll let you take over, but let me just say yes. That's a very good question, a very good thought, and you can attempt to take advantage of the astrophysical existence of big magnetic fields around neutron stars, and see if axions convert in those environments. So you might find a photon line, a microwave line coming out of neutron stars. People are looking for that, and of course, it's much less controlled than looking in the laboratory, but it's not completely out of the question that could compete. So maybe, Luca, you'd like to say a more.
Yes. So, comes with a lot of asterisks. That's the issue. Like, how do you model neutron stars? How many of them are there? What's their distribution? So all of this comes into not having the clean laboratory built at Earth. But in principle, yes, it goes through the same idea of resonance. So you have the plasma surrounding a neutron star is basically creates the environment such that you can have a resonant conversion of an axion that is the dark matter. So you have dark matter that falls in the gravitational potential of the neutron star, and within some region, it converts. It matches this resonant condition such that it can convert into a radio signal, because as we saw before, micro electron volt, tens of micro electron volt falls in the order of 10 gigahertz range. So you need to look at this with radio telescopes. And this is what people have done, have either looked at archival data or have taken new data from neutron stars observed in the right radio band in order to look for this type of signal. So there's some literature, and there are experiments that are ongoing for this.
Okay, if you're interested, you can talk to Luca afterwards.
Yeah.
So, any more questions?
This idea of this alpha experiment looks very interesting. I wanted to ask about these wires. About this,
Yes.
is this where the magnetic field is localized, or what is the role of the wires? Like gives a mass to
The
photon,
wires
but
have.
what is the physics that?
It's the physics of plasma resonances. So to oversimplify a bit, in a metal you would have a plasmon, which is the photon acquires a mass, but it's too big. So to make the mass smaller, you make less metal. But it's a little. The actual theory is a little more complicated than that. But the basic idea is you have electrons moving along, and they produce magnetic fields which couple to the other wires. There's a collective response. These kind of wire metamaterials have been produced and studied for many years for other purposes. They're used in magnetic resonance imaging to enhance the quality of things, in interfering with radar. So there's quite a bit of engineering practice, which I didn't know about, but we came across as we were exploring these ideas. Yeah.
Thank you. Yes, I also have a question for this.
Yeah.
So, speaking of large magnetic fields in condensed matter physics, usually if you give some pressure to a material, sometimes you can generate so-called pseudo electromagnetic fields, which is huge. Like if you estimate that it can be the order of 1,000 Tesla in materials just by pricing the materials. So maybe that can also become another possible route.
There's plenty of room for creativity in this subject, I think.
Okay.
So we know the equations, and we know a lot about, of course, materials that have different electromagnetic properties. So
Yeah. Any more questions?
Yeah.
So if more questions, please
all right.
continue.
So let me now show you that axions have been discovered already, but not the free space axions, but rather emergent axions that appear in materials. So remember, A was the coefficient of E dot B. And if you have materials with different values of that coefficient, it's as if you have one value of the axion field inside, another value outside. And so in those equations, you have a discontinuity, a spatial discontinuity in A, which means where there was a gradient of A, you get a surface delta function. Okay, a discontinuity turns into a delta function now at the surface. And so we can interpret what happens in those equations. We find in that situation where we have a discontinuity between materials that have different values of the coefficient of E dot B, we get surface effects. Okay. Now remember, E dot B is neglected in electromagnetic texts because it doesn't contribute to the bulk equations of motion. But materials have surfaces, and you can have junctions between surfaces, and then the difference of the A between the inside and the outside is very much observable and gives striking surface effects. So here we get a magnetic field inducing charge density, and we get a surface Hall effect. Topological insulators are characterized by, in fact, having, relative to vacuum, an E dot B term with A having a certain quantized value. So the theory predicts there's a jump in the value of the A field that is related to fundamental constants. And when you have that kind of jump, you get these surface Hall effects, and they modify the properties of light interacting with that surface. And in fact, they give two different effects that are potentially observable and actually observed. That is the Faraday effect, which is when you propagate light, polarized light through, the plane of polarization rotates. And the Carr effect, this is not the curve black holes, this is Carr, an experimentalist, that if you bounce the reflected light, also has a rotation of the plane of polarization. And the theory predicts the magnitude of these effects. Really, the theory predicts the magnitude rigorously quantized at zero frequency, but the frequencies of light are still small enough that you get approximate quantization. So you can express the predictions in terms of fundamental constants. And in this paper, they use this to measure the fine structure constant to within less than 1% by looking at macroscopic effects like this. So in the same spirit as the Josephson effect or the quantized Hall effect, where materials lead to material properties have values that can be expressed in terms of fundamental constants. This is another of that very distinguished set of experiments. Okay, so that ends the discussion of part 4. And
Question?
other, yeah.
So I just have a question on the timeline that you have in mind for alpha.
Well, alpha is being built now. Should start taking data within a year, according to the estimates, and significant data in 3 years. And it has a 5-year. We're supposed to deliver on those estimates in 5 years. Right.
Thanks.
All right. Okay, now I've now discussed parts 1 through 3 of the lectures, which were originally planned to have 5 parts. So I won't be able to cover anything like all the material, and time is limited, and I'm getting a little tired, frankly. So I'm going to just hit a few high points. I will, in a few weeks later on, develop this material more fully and give lectures like this at MIT, and then at Arizona State. They'll be recorded, and then we'll make sure that they're available to you as well. Okay, so I was just looking over what I wanted to pick out of all this stuff as a conclusion. So I will discuss some but not all of the material that's on these slides. So the first thing is mechanisms of spontaneous breaking in matter, breaking of time reversal, but also other symmetries, just very general. And the one I want to discuss in a little bit of detail is what's called spontaneous symmetry breaking. And we say we have symmetry when a symmetry breaking in a material when the material displays less symmetry than the fundamental equations that govern it. And there can be different kinds of symmetry breaking. And let me discuss just the most developed and the kind of symmetry breaking that has the richest description in physics. That's spontaneous symmetry breaking. So this has many, many examples. The formation of crystals breaks translation symmetry and occurs spontaneously. The formation of ferromagnetism and other magnetic structures, anti-ferromagnetism, very more elaborate spinel structures and others, ferroelectric structure, which I'll say more about, and superconductivity, which in a sense breaks gauge invariance, but more precisely is a perturbed form of breaking of conservation of electron number. Spontaneous symmetry breaking has several characteristics that are profound. And let me just go through those briefly. So the mechanism of spontaneous symmetry breaking in broad terms has been known for a long time, but it's worth recalling because we want to see, we'll be talking about macroscopic consequences, but we'd like to at least make a gesture towards how they arise from the underlying microscopic theory. And this B is not supposed to be there. Okay, so to understand ferromagnetism, we have an effective spin-spin interaction. This already is interesting. The fundamental magnetic dipole interaction is about 1,000 times smaller than appears in this microscopic theory of magnetism. And it was a great triumph in the early days of quantum mechanics to explain the form of this interaction based on quantum statistics. That it was not directly an electromagnetic interaction, but a manifestation of kind of the unofficial fifth force of physics, which is quantum statistics. Okay, and then the yoga, the procedure where you see spontaneous symmetry breaking, is you make an assumption that the spins that do want to, if J is negative, say do want to all align in the same direction, but don't know which way to do it because the theory had the system is symmetric. You assume that they do make a choice. They organize themselves into making a choice and see if that's actually advantageous. So you assume what's called a local field. The local field will induce a field at a local magnetization, and then that will induce a preferred direction for the magnetization of the focus of interest, the point of interest, that you can calculate. And then you can apply self-consistently. See, if you assume that the field, the spins are acquiring that magnetization as a result of what the other spins are doing, you can see if it all adds up. Okay, so this is the master equation. In the context of superconductivity, it's called the gap equation, but it has a much older history. And if you impose that you can construct a candidate for how the system organizes itself, and then you can check if that's favorable compared to just random disorder. Okay, so this is probably familiar to most of you from textbooks of statistical mechanics, but it's quite profound and supports many variations. And we'll at least allude to some. This is the magnetic compass that I've referred to several times, and I love this idea, so I will mention it one last time. The yoga of the magnetic compass, which has been known for hundreds of years. I mean, the magnetic compass has been known for hundreds of years, but not really how it works, its profound meaning. And actually, I was very moved as a child, before I knew anything about physics, reading Einstein's autobiography. He refers to when he was a child being introduced to a magnet, and that seems so mysterious and so interesting that it really got him thinking about the physical world in a new way. So I hope you find this inspiring too. So the point of spontaneous symmetry breaking and the fact that it emerges in the kind of self-consistent way where all the neighbors have to agree to do something in common, even though they could have done something else, they settle on one, is that because they've settled on one, and that agreement percolates through the whole universe of the material, it's stable against all kinds of local perturbations, because off at infinity, you'll get the information to realign. But it was an arbitrary choice of direction, and so it costs zero energy, as long as everybody agrees, to change the direction. So you have sensitivity to this kind of global perturbation, but insensitivity to a wide range of local perturbations. That's the lesson of the magnet. This is a slightly vague but much more generally applicable version of what's usually called the Goldstone theorem, or the Nambu-Goldstone phenomenology, where you have spontaneous breaking of a continuous symmetry giving you long-range excitations of low energy. If they're very low frequency, that's like changing the magnet by applying a magnetic field, and a constant magnetic field, or a nearly constant one, and that will cost very little energy to make the magnet move. Okay, I'll skip this one. And I'll skip all this. It's very interesting, but not as interesting as what I want to say. Maybe I'll just mention this idea. How do I go back to plane? That. Okay. Another form of symmetry breaking that's not what's usually analyzed in physics, but arises very much in biology and other contexts, and also chemistry usually, and in physical situations, is competitive symmetry breaking. That's when you have different alternatives that are, in a sense, equally good from the point of view of fundamental interactions, but they compete for common resources, and whichever one gets started first takes over. So competitive symmetry breaking. So this is a kind of thing that can happen when you have phase separation. For instance, famously, if you have a solution of some material that can crystallize in either right-handed or left-handed forms, okay, you will get crystals that are sometimes left-handed, sometimes right-handed. In repeated trials, either one is equally likely. But in any one trial, you get just one if you do it slowly. Another nice example of competitive symmetry breaking is driving on the right side of the road. Okay? It doesn't matter if you drive on the right or the left, as long as everybody drives on the same side. And people who drive on the wrong side will be eliminated. Unless they're in England, which is sufficiently isolated that everybody can drive on the left there and not have collisions with people on the continent. All right. Okay, so anyway, I think this idea of competitive symmetry breaking deserves and could benefit from more work in physics, and it's certainly very important in biology. And seeing the relationship between that and spontaneous symmetry breaking could be very fruitful. I think in the limited time available, I will concentrate now on discussing the phenomenological consequences of microscopic time reversal violation in matter. The big thing that I'm looking forward to, but I won't have time to explore here, is that one form of matter is biological matter, and there's a very interesting question whether biological matter supports, in an important way, violation of time reversal. We know that biological matter supports violation of parity. We know in many cases that left-handed molecules have different biological activity than right-handed molecules, even though physically they're equivalent. And there's a very live question about the analog for time. Okay, in any case, in matter, magnetism in general violates time reversal symmetry. The magnetic field is odd under time reversal or unnatural. However, all by itself, that really is not the death of time reversal symmetry in magnetic materials because, okay, time reversal changes the direction of the magnetic field, but so does turning the material upside down. So there's a modified version of time reversal symmetry where you both change the direction of time and make a rotation that's still obeyed by the material. Or in antiferromagnetism, you have alternating directions of spin instead of everybody agreeing. And that certainly breaks time reversal, because if you apply a time reversal transformation, the spins both change. So it's different. But the average magnetization, the macroscopic structure is zero, and that does not violate time reversal. Okay, so can we get forms of time reversal that are less disposable? And how will we tell when we have them? Okay, so here's a kind of time reversal symmetry violation that you cannot argue away. It's a scalar quantity, and if you have consistent choice of a non-zero value for the alignment of electric dipole moments and magnetic dipole moments, that violates time reversal symmetry. Okay, and you can't undo it by rotations or anything else. It's really just violates time reversal. Another one is the static response, which I will discuss, and another one that I will discuss in some detail because it's interesting and very worthwhile for students to know and powerful in other domains, is how you analyze the propagation of light and the implications of that for the implications of symmetry in that context. Okay, then there were another number of things that I won't discuss that are also signatures of time reversal or not in materials. So let's first discuss the correlation of moments, which I think is the most basic phenomenon. So moments show up macroscopically as polarizations, and that's something you can measure through spectroscopy or through spin resonance. If you think about it, if you have a bar magnet, that of course has a magnetic dipole moment, they have to come with a label, N or S. If you were in a dark room and didn't know whether the magnet was NS or SN, there would be no experiment you could do without that would tell. You couldn't. Okay, it would point some way in alignment with the magnetic field, but if you were deep under the ocean, and you wouldn't know whether the magnetic field was this way or that way, because the bar magnet is unlabeled. But if you had a dipole moment, that would provide a label. an electric dipole moment, because it would tell you which way the electric dipole moment is pointing, and that way you could sense the direction. So in effect, that provides a label for the compass. And if you're a bacterium that can't read N or S, and N versus S, having a labeled magnet like this is what you need for navigation in the dark under the sea. And maybe as a culmination of this discussion, I will show you pictures of these so-called magnetotactic bacteria. It's very interesting that this kind of correlation is something that is observed and is an object of very intense study in condensed matter physics these days. Multiferroic condensation, where you have magnetic polarization. So that's ferromagnetism. That's where the ferroic comes from. But you also have electric polarization, which is usually called a ferroelectric, even though it's not iron anymore. And multiferroic is when you have both. And okay, so the existence of moments is one thing, and you can access the moments, but you can also do macroscopic experiments that should be pretty simple to do on a large scale with many materials to see if you have a breaking. And this is very, very clear cut also. And this is the manifestation of the famous E dot B term that we're so exercised with, and say it doesn't affect the classical equations of motion when you make local variation. So it doesn't change the local equations of motion that you use to derive the classic Euler-Lagrange equations of motion. But if they extend over all space, you look at the derivation there, you drop surface terms. You can't drop the surface terms, and having an E dot B term means that having an electric field aligned with a magnetic field either costs or gains energy for you. And that means that if you apply an electric field, you'll induce a magnetic field, the lower the energy. Or if you apply a magnetic field, you'll induce an electric field. And that's manifestly T-violating, right? Because B and E transform in different ways under time reversal. So, in particular, as a practical matter, we can apply big magnetic fields and see if, under the influence of a magnetic field, our material becomes something that has a non-zero polarization, whether it's a ferroelectric induced by magnetism. How do we actually see whether something is a ferroelectric? Well, it's not completely straightforward, and because if you have an electric polarization in bulk, that will induce surface charges, but surface charges can be discharged by having stuff accumulate on the surface, and that's energetically favorable. Having concentrations of charge is a very bad idea energetically. But if the material involved is connected to a capacitor, you can collect the charges that happen as you change the polarization. And so if you have a ferroelectric response that is dialed by a magnetic field in particular, you can watch the flows of charge off its surface as you vary the magnetic field. So this is an example here where this is ferroelectricity modified by pressure, but the same idea would apply to ferroelectricity modified by magnetic fields. It's called the Sawyer-Tower method. Okay, so now let me discuss the propagation of light. The asterisk here means, of course, it's not necessarily light. It's something that obeys the equations of light, if you like, or electromagnetic waves in general. So the classic signature of parity violation in solutions, and so a characteristic signature for the biological origin of a solution, the idea of which goes back to Pasteur, the discovery of optical activity, is that if you have a material, a solution that contains primarily one-handedness of a molecule rather than another, that will rotate the plane of polarization of light as light propagates through. That's optical activity. And what I'd like to do here is show you that this can be treated advantageously using the modern methods of theoretical physics and effective Lagrangian. Okay, this. So this is maybe overkill for any particular application, but it's a generally powerful tool that you should know about. And it's a very good tool for thinking about new situations. And once you've mastered it, you can play a lot of variations. So let's consider the implications of adding this kind of term to the standard Maxwell electrodynamics. Okay, so the rules of this game, the good taste in effective Lagrangians is you consider possible interactions that are simple, that are of low dimension, and that obey general principles, like in this case, rotational symmetry and gauge invariance. And there are only a few such terms, so you can sort of classify what the interesting possible effects are. Now, this one, although it respects rotation symmetry and time reversal, violates parity. Right? Because we have two vectors that are unnatural under parity, one that's natural. So altogether it's natural, but when you have a product of three vectors, that's change of sign under parity. So this is the natural thing for three vectors to do, is change sign when they're contracted with an epsilon symbol, if you like. And so this interaction is parity odd, but it's also, and it's time reversal even. Okay, so it breaks parity, but not time reversal. And if you look into the Maxwell equations, you'll see that, of course, this does not even communicate with the electric field, so it doesn't produce any effective charge, unlike the axion. But it does, when you derive the equation of motion by varying the vector potential, this contributes an extra piece, which is easily calculated, and it's this. So it generates that kind of emergent current. So we get these modified Maxwell equations, and now if we use Fourier methods to solve them, so put in a plane wave solution, the derivatives become algebraic operations, and we get a very manageable analysis. Okay. We find that we get, not surprisingly, we have transverse waves emerging. This comes out of the del dot E equation. del dot B equals 0 and del cross E equals 0 are identities once we've decided to use vector potentials. So those are automatic. Del dot E is this one, and del cross B here is this one. Okay, so it's really, really simple to analyze. And I invite you to compare this treatment to the treatment in standard books about optical activity. This is the royal road. And now if we want to think about propagation in a particular direction, okay, we're advised to look at polarizations which are orthogonal to that direction, transverse polarizations, and we need to satisfy this equation. So if we choose circular polarizations, sort of guided by the eye here and the fact that things rotate, that inspired guess diagonalizes the propagation. So the circular polarizations both travel at definite speeds, but they travel at different speeds. And that, if you think about it, is optical activity. Okay, the circular polarizations travel at different speeds. So the originally linear polarization will rotate. The nice thing about this approach is, well, a nice thing about this approach is that we're calculating optical activity from an effective Lagrangian, which is just a contribution to the energy of our material or atom or whatever. And so we can use just second order perturbation theory to calculate that. So the kind of hocus pocus you see in old books about optical activity, make it look very obscure and difficult, can all be bypassed and just use second order perturbation theory to find the effective Lagrangian. So it separates the microscopic considerations from the macroscopic considerations very nicely and cleanly. Okay, and there's some pictures of optical activity. If you shine light through glucose and look at how, so light is going through glucose, and then you rotate you have two polarizers and you rotate their relative position, and the optical activity is wavelength dependent, and so the color changes also because the polarized light getting through, the kind of polarized light that gets through depends on frequency. This is an experiment you can actually do at home with some, if you have a laser and polarization plates, but you can just use sugar water. Okay, anyway. Related to this, and we can do it very quickly, so I will, is the magnetic Faraday effect. That comes from this term in the Lagrangian. This doesn't violate any symmetries. But if you have a background magnetic field, you're getting something that looks very much like the optical activity we had. And you can analyze it in the same way. And this is a famous effect discovered by Faraday of rotation of the plane of polarization as light travels through a magnetically active, a magnetic field in a material. And then finally, to get a T-violating effect, to test for T-violation in the material, we just change magnetic to electric. And then an electric Faraday effect would be a sign of time reversal violation. Okay, so then you can also look at other effective Lagrangians. E dot B, if it's E dot B, doesn't contribute to the bulk equations of motion, but if it's not E dot B, but a more general tensor form, as you might get in a crystal, then it will. And that's one of the things you can do. Okay, but so that gives you, I hope, some sense of the many ways in which you could try to access time reversal violation in material on an industrial scale. Very simple experiments that you can and test and hone in on any suspects.
Nothing to do.
Okay. Whoops. No, this is the previous lecture, so no, this is not, that's not what we want.
So,
Yeah, and very close to the end here. There's something in the cloud. Okay, something in the cloud does not like multiferroics, but if we're patient, eventually you can get it through the sensors. Okay, so multiferroics are materials that have both electric and magnetic polarizations. And all I wanted to say is that these can be described in the framework of Landau-Ginzburg theory, or if you like, if you start from microscopic theory, low order perturbation theory, to see whether these terms occur. And a term like this, magnetic polarization, electric polarization dot magnetic polarization squared in your energy, would encourage a non-zero value of P dot M. It doesn't tell you which value to choose, which is typical of spontaneous symmetry breaking, but you have to choose one. And so this is sort of the necessary and sufficient condition for getting the alignments of moments. And all right, so let me conclude this whole series by introducing you to a very interesting cast of characters that
where should we go?
the next lecture,
Oh, next lecture.
number 5,
Okay.
number 6 rather, and okay. All right. No, I don't want to use all of it at all. Where it's getting pretty late, and so I just want to do a fun thing. So, parity violation in biology is a very beautiful potential subject, an established subject, and time reversal violation in biology is a beautiful question. But it deserves more than the cursory treatment, so I'm not going to attempt to rush through this material. But I do want to show you as kind of a beautiful illustration from the natural world of some of our themes. Magnetotactic bacteria. These are truly amazing creatures. Remember, I told you we wanted a labeled compass as an example of T violation, and that would be useful if you had to determine the direction of a magnetic field in the dark, and if you didn't know how to read. Well, here we go. These magnetotactic bacteria manufacture from the surrounding water. They distill it out and make these what are called magnetosomes, little magnets that are remarkably perfect, single domain, and they align them here to turn themselves into magnets. And then they can align with the Earth's magnetic field, and in that way passively figure out which way to go, because they want to get themselves into a certain region within the ocean where the conditions are particularly favorable for them. And if they didn't know how to orient, they would just wander around diffusively and have a very hard time finding the right place. But if they can follow a magnetic field direction, they can hone in on it very efficiently. And that's what they do. And here is sort of inside a magnetosome, and it's a labeled magnet because the two sides are different and the polarization is fixed by how the thing develops. So you get a labeled magnetic moment. And there's a lot to understand about these things that is quite fascinating. A few highlights are that they use magnetite, the most powerful naturally occurring ferromagnetic material that's abundantly available. Their product engineering is excellent. They produce high uniformity and uniform size of the little crystals. They are primitive prokaryotic organisms. That is, they're single-celled and they don't have a separated nucleus. So they occur very early in the tree of life, have very likely an early evolutionary origin. So life learned very early on how to break time reversal symmetry. And it probably is still making use of that trick in many other applications. This is yet to be proved, but is is hinted at by the fact that iron is used as a cofactor in many important pathways of reactions, often in closely related but differently packaged forms. So these magnetotactic materials may have a lot to teach us and may have taught us deep lessons already that we're not aware of. And with that, I think I will conclude. We've covered an enormous amount of ground, going from profound principles of fundamental physics to entertaining examples to potentially new ideas and applications in materials and even in biology. And I hope you've enjoyed it, and there's much more to come and much more to explore. Thank you.
Okay, thank you, Frank. Yeah, thanks for this very comprehensive review and also inspiring lecture series on the temporal symmetry. So now we are open to questions. Any questions from?
Yeah.
Professor, the Lagrangian describing the axion for four-dimensional space-time on the boundary is the Chen-Sums theory. We know the Chen-Sums theory is related to aliens. So is there any connection between alien and axion?
Is there a connection between anyons and axions?
Yes.
Well, yeah, they have a common inventor, or the words at least have a common inventor. You're looking at them, and the concepts are closely related. They, as you said the maybe the most basic relationship, which is if you take a notional four-dimensional material that has the axion term, the characteristic A E dot B term, and cut it off in space or in time, you get Chern-Simons terms, which are the kinds of terms that link charge to flux and are the heart of anyons and fractional statistics. So that's, you said it, that's the connection. And there, you can play with it in different ways, but that's the core connection between them. Yeah.
Thanks.
All right.
Okay, thanks for the question. Any more questions?
Okay, Professor, I want to ask a question about its model. As we all know, its model is the simplest magnificent model. And
which I'm a little, what model?
Its model.
Ising model. Okay.
Ising model.
Ising, whatever. Okay. Speak a little slower. I'd have a better chance of understanding.
If we introduce quantum theory into Ising model to change the classic model, what do you think of the quantum networks can play a role in this Ising model?
Well, can quantum mechanics play a role in the Ising model? Well, sure. And the Ising model itself is a little difficult to treat within the framework of quantum mechanics, but the Heisenberg model, which is kind of works with quantum mechanical spins, is in the same spirit as a model of magnetism and matter, and is a very rich subject that people study to this day using advanced numerical techniques as well as experiments. And the whole subject of magnetism within quantum theory is a profound subject with many applications. And maybe worth saying is that you can't understand magnetism without quantum mechanics. So even though the ancient Greeks already found that you have magnetic materials, and they were puzzled by it, it's only in the 20th century that there was even a remote chance of properly understanding it. Yeah.
Thank you.
Okay. More questions? So
I should just say, besides the ancient Greeks, there were the Chinese people who had this magnetic spoon-like object that obviously also
I see in the picture. There's a Chinese character.
Yeah, that's from ancient China. Yeah.
About how to make Ising model become a quantum model. You just simply apply a transverse field that is perpendicular to the Ising direction, then will cause the fluctuation along the field direction. And because the non-commute nature of these two spin directions, it becomes a quantum model.
Yeah. So enriched versions of the Ising model can support interesting quantum phenomena. Yeah. Okay. I actually discussed that yesterday at the workshop on quantum simulation, the transverse Ising model and metastability and first order phase transitions and false vacua in that context. You know. So there's still quite a bit of life in that business, and a lot of this. You know, we had world leading researchers from all over the world talking about quantum simulations of magnetic systems. So even fairly simple ones are at the frontier of what can be understood quantitatively.
So more questions from students? Okay, so maybe I comment a little bit as a last. So I think it's Feynman or maybe said that the physicist is a magician in a straight jacket. So I think the important message for students is that you should enjoy physics and play with it, and eventually it will reward you. I think Frank is a very typical, very good player in physics. So yeah. So with that, let's conclude this series. So and thank you very much, Frank.
Thank you.
For this talk.
Thank you.
Okay, now we have some.
Before we finish, we have 3 small issues. So our lectures are broadcast online. So besides this offline attendees here, we have many online attendees. One of online attendees who is in Boston in MIT, she want to share a movie with us, with Frank.
Oh.
Hello, Juliana.
I think.
Hello. Are you ready
Hello.
to show the movie?
Yes, I'm ready.
Okay.
Okay. Can you see the screen now?
Yes,
Yes,
we saw the movie,
we-
but the voice is.
Your voice is very soft.
Okay. So we'll start right now.
Point to draw before your eyes one of the recent glories of QCD,
Okay.
and then something about what we hope is the future. One of the recent glories of QCD was to make it possible to discover in a very noisy and hostile environment a very small signal called the Higgs particle, which people found pretty interesting. And finding it would have been utterly inconceivable without QCD. And the underlying process is quite fascinating from the point of view of fundamental physics. It shows QCD in action at several stages. You start with protons. You analyze in terms of gluons within protons. The gluons, in order to communicate with the Higgs particle, because light particles don't like to communicate to the Higgs particle, they do it through a virtual loop. Quantum mechanics comes in. The Higgs particle very fleetingly exists. It's drawn in gold here. And then it has to communicate with light particles in order to decay. And so it also conveniently sometimes decays into photons, and that was the original signal indicating a small bump on top of a huge background. That was the discovery of the Higgs particle. And without QCD, it would have been inconceivable, literally, to think about this process, much less to calculate reliably what to expect and to interpret the tiny signal that people fished out of roughly zillions of events to get a handful that statistically identified that it was something extra, the Higgs particle. So that was the past. Now we're trying to do something even grander. That is to, from hints provided by fundamental physics, allow the astronomers to identify their mysterious dark matter in terms of a tangible particle. The particle is another golden particle called Axion. And it, according to fundamental theory, by the way, its motivation comes out of the deep structure of QCD. We understand that it will couple to two photons from fundamental theory. We wanted to convert into a single photon so that we can observe it, and we want to help it along because the coupling is so weak. So we replace one of the photons by a strong magnetic field, and then in the strong magnetic field we have a resonator that also encourages the photons to emerge, and the axion, with all this encouragement, once in a great while turns into a photon, and then our eyeball here can observe it. QCD makes a problem, QCD solves a problem, and in the process, it tells us possibly what the dark matter of the universe is, and in any case, how to have a great intellectual and scientific adventure trying to find out.
So this paper was published in November 15th, 50 years ago. So just in this week, 50 years ago. So this seminal work became a milestone in physical history. Congratulations.